2 H02 prime plus H12 prime equal F3 F4. So this actually I have a full integral. So where actually you can see in principle F(I) equal F(I) with 1, 0, the positive word. But I cannot, this is most general. This should be actually equal constant. Can you see y equal constant? Or maximum depend on? I think it should be constant. You say why? Because remember, this guy is only function of u, right? This is our beginning. So how they can actually, if each of them function of u, we cannot get this way. So in any case, even it's a constant, we say y r go to infinity, we do not have Gravitational wave, right? Remember, we consider finite sources. In the infinity, all of them equal 0. So if we consider infinity, all of them 0, this constant has to be 0, right? So this actually, this is the general case, but if r goes to infinity, which we say we are far, infinity far from sources, then h prime a b go to 0, which actually lead us f a equals 0. So I get actually simply put it in 0, 0, 0. This 0, right? Yeah.
We did an approximation that we are taking. For that, we do not consider R tending to infinity. We consider R to be large, but not infinity.
Yeah, you can consider it too large, but for example, this actually, if I have the sources here binary, so I'm actually here, but if I extend the gravitational waves, go to infinity, this definitely will be 0. I'm only in the, not infinity, but I'm in the middle. But the gravitational wave will continue, right? Will continue so until 1, until near the boundary, in principle, right? But if I really go to infinity, this guy is supposed to be 0 because, you know, it's 1 over r unless it decays, right? So that's why, if I take that limit, this is f(I) test. So this is actually the case. You see, if I equal 0, I can find my, let's see, I can find my 0, 0, and remember here, x prime equal eta ab h prime ab. This actually equal h prime 0, 0 minus h prime 1, 1 minus h prime 2, 2 minus h prime 3, 3. Right? This is our definition. So you just actually write this 4 equations, so 1. So I should actually, I'm able to express 4 of the components in terms of others, because I have 4 equations, right? So by doing this, what I'm going to like write it down. Here I will write prime 1, 2 equal minus h prime 0, 2 h1 3 prime equal minus h2 3 h01 prime equal minus 1 half h0 plus h11 prime h23 prime equal minus h22. So this actually the 4 equations, the 4 constraints allow me to write this 4 components h1, 2, 1, 3, 0, 1, 3 in terms of the rest. Okay? So what we did is the following. We solve the Einstein vacuum equation in h prime coordinates. And then we get waves perpendicular along x direction, right? So we have, in principle, we have 10 components. Because the HAB, the symmetric, is supposed to be 16. But 16, because the symmetric, 16 minus 6, actually, you can figure out the 10 components. 10 components, now I'm using my Gitter residues. I have, remember, corner transformation XI. Using that one, I find that this actually comes from prime A, B, A equals 0. I find the 4 components can be read in terms of the other 6, right? So from 10, I reduce 6, right? But we know Gravitational waves have only 2 independent components. This is a very important point. Lots of time in university, people ask you, I have a 4 arbitrary functions, right? Corner transformation. So HAB has 10 components. What do you mean you have only 2 components? Where are the other 4? 1. So this is exactly good. So after this class, I would like you, if somebody asks you, you can really explain to them, we have indeed 2 components. Because other 4 Gitter residues. You see here, this is actually not so easy to understand. In principle, I have 4 arbitrary functions. Each one related to the corner transformation x0, x1, x2, x3, right? So HAB has 10 components. How can you reduce 10 from actually to 2 by only 4 arbitrary functions? But we have a Gitter residue. That's actually fast. So this actually, from 10 to 6, now I'm going to use in this Gitter residues, make another transformation. But remember, this guy is equal to 0. This cannot be n. This certify this one. That's fine. You see, certify this one. Remember, we consider plane Gravitational waves along x direction. I simply actually assume my x a equal x a u prime, right? Because this is a wave. Then you can see this certified situation. This is because this actually equal what? D squared psi hat a du prime dy prime equals 0, right? This is the same equation. This actually in terms of x, t prime x prime in terms of u prime y prime. If my psi hat is function of u, dy prime, d psi hat equals 0. So this you need a solution, right? But this tells us this guy is the arbitrary function of u prime, right? So we have to do this step by step, 100% physics. Mathematically, you cannot make any approximation. What we really make approximation is epsilon. But here is regular physics, mathematics, right? So this actually needed this, the solution of this is the Gitter residue z hat a. I'm going to use this 4 arbitrary function, which is a function of u prime only. But this Gitter residues, although not actually general as z hat a, this is enough for me to kill 4. Why? They are function of the only u prime too, right? So here is the u prime, now here is also u prime. This allow me, this arbitrary function u prime, you can immediately say, allow me to kill 4 for this actually, 6. So that's why I'm going to reduce it to 2. Any question about this part? So I would like you guys to see the logic. So we are doing some, although we are doing some approximation, we are doing approximation. But the mathematics is regular. Regular, I mean, thinking this actually is a function of this I did not make any approximation why I eliminated the components. This is 100% precise, right? So if I do this,
Professor?
yeah,
So there are only 6 physical parameters, or among them there are only 6, and these are for some gauge choices which you perform.
yeah, this I can remember when we come down to X prime coordinate, we still have this giga radius, which means that if I make a coordinate from further coordinate from this one, my phi prime set over to this phi prime will describe the same gravitational field as this guy. There is no difference. So remember when we consider GIAN, electromagnetic waves, if we use, let's say, A mu and A mu prime equal A mu plus E mu lambda, this guy's E equal E prime, right? The magnetic field will be the same if you use this one. This actually is the corresponding magnetic field. Let's see, I'm using the super vector. This super. They are actually equal. There is no difference. And also the B field equal B. So the same idea. So this is the potential, but the magnetic gravitational waves will be the same using this one and this one. Of course, also the same way. AB, right? So this is actually sure. They describe the same gravitational field. The only difference, when I talk about this one, this case has no giga radius. I just take everything due to the artificial coordinate transmission. Now, from here to here, we just take a part of them away. But we still have this giga radius. We needed to take this part also away. After we take all of them away, the rest here, this is the physics. This is the gravitational waves we are really want to measure. This is the wave part of what we're going to measure. Okay? Any other questions? So I do not want to rush this part. Because the perturbations you see here, this is for gravitational waves. When you started black holes perturbations, our couldn't work on this. So you will find it equal. You need to take all the giga radius. Otherwise, when you talk about polynomial mode, those things, that polynomial mode can be artificial from the coordinate perturbation, right? So when you consider from the cosmologies, our universe, the principles homogeneous autotrophy, I think you ask me later on, I will answer. So the homogeneous autotrophy, this is the first approximation. Our universe is not homogeneous autotrophy. We see the galaxy. We see actually a large scale structure. But the good thing is, this can be just simple linear perturbation. If a linear perturbation is sufficient to explain our whole universe. At the very beginning, when I was studying cosmology, I didn't believe this. This so complex universe. You can use homogeneous universe as the first zero-order approximation, then consider all the galaxies large structure formed by a linear perturbation. This is a very broad assumption, right? But so far it still works well. Okay? So this accuracy. What about here? The same thing. Okay? So now I'm going to use the giga residues actually to narrow down further. There are only 2 independent compounds. Now 0, 0, 0, 1, 0, 2. Then see, if I purposely choose this guy, I will kill other 4. Okay? So this is logic.
So
Yeah.
that by
Sorry?
That choice is unique, how do we know?
That choice is not unique, but the degree is unique. Right? So you can, for example, you can choose Q, let's say, I'm going to choose Q H00, H01 out of the question, only leave H22, H23. You can choose others. But the since the physics does not change the two opposite functions. So this work is okay? Yeah, good question. So why I choose this one? Because after I choose this one, I can easily get a physical interpretation. Maybe you can have other choices, but you have to be careful with your interpretations. Yeah, this is the thing. So the physical work is the same. Yeah. Very good. So what I'm going to do, actually, you can see, I'm going to choose the following. So this is the four. I'm going to use this one, choosing zeta prime 0 hat u prime equal 1/2 h00 prime u prime. This actually give me, I have this operator function, I can always do it. But this is the derivative of this means that this d h at 0 d prime d prime. This actually similarly give me the function of u as an integral. I get maximum data constant. It's fine. So I will choose this one. Then also the second point, I will choose this. Prime is again u prime is equal minus 2 h11 plus 11. This prime, sorry, this actually is in the x prime coordinate. Huh? We have too many primes, so this actually that 2 prime in. So this prime represents the derivative. Huh? This is actually part prime equal h02 prime u prime 3 prime u prime equal h03 prime u. So if I choose this one, I simply choose it. Then I have, then you can prove, then you use actually this. This is a t x, y, z, the current, right? You will see this is 0, 0, 0, 0, 0, 0, 0, 0, 0, h22, h23, h23. Because this is 3 to 2 is symmetric, and this actually minus h2. So I forget the number, we call this, let's say, 17? Sorry about it. So let's call this 18. So I have actually 2 components. So means by just ask the question, what about if I choose different? Choose different, you don't have different components. Well, the reason why I choose this one, because I can easily get the physical interpretation. So you can choose different, but then you have to be careful when you interpret the component. Right? Yeah.
One question. When we are actually observing,
Yeah, observing.
two components, right?
Well, yeah.
So, are are we in the process of observing, are we actually putting our setup such that these gauge conditions are actually satisfied?
Yeah, this actually, you see, we are using, mathematically use the gauge residue to fix all the gauge, like what we do actually. This E prime E and corresponding are all equal, but it's only the potential. So when we are doing this, we are left normal gauge choice. Your current component fixed, right? So this component is what you are going to observe. You are asking, this is exactly what we are observing. That's actually observational question. So observational is very complex. Why? Because you can see we are observing, let's say, if we put a light on Earth. Light on Earth, remember, the vertical coordinates is connected with CMB. CMB define a perfect coordinate. What means CMB? When we consider the micro background radiation, this is actually electromagnetic waves. We want to say this is, in that coordinates, the CMB is the corresponding fluid is a community. That define our very ideal observational current. But now you narrow down to our galaxy. Our galaxy is moving in terms of CMB. So we know, by observation, we know what's the relations. Now we know our Earth is moving relative to the Sun. Our solar system is moving relative to our galaxy. Is our galaxy in the center? We're in the 2/3 of the center, right? So you have to take all the effects into account when you do real observation. This is totally different thing. I'm doing here pure theoretical. So we just get rid of all of the gauge choice from X to X prime to X double prime. This is theoretical. Okay? So I didn't connect with real observation. Connect with real observation is more complicated. You need to, like what I said, take out all the effects. So the really ideal coordinate will define is where the CMB is under rest. That's the universal coordinate.
So you are saying that this choice of these functions is not affecting the observer's dynamics?
No, this actually we're purely theoretical. We are not really connected with observers. Theoretically, we take off the gauge residue. So how you connect with observers, this is totally another different segment. That's actually a reason between observers and theoretical. So here we just do all pure theoretical. Okay. So now to answer another question, this you can see, this is actually like a gauge choice. If you really define the next thought we're going to consider, using geodesic deviations, that will independent of your current choice. That's exactly giving you precise physical. So that's why I think I like that part. So I just spent 4 years to, I was working with colliding waves. So in order to see, I found there's actually, electromagnetic wave, we have further rotation, but Maxwell equation is linear. So that when you see, I have electromagnetic wave pass through a medium, let's say like water, then you have an interaction because social term interact with the electromagnetic waves. Then it changes the direction. But if you just simply two electromagnetic waves, there's no interaction, no charge. So they just simply pass through. What about the gravitational waves? Gravitational waves, each one has a mass. So the Einstein equation is non-linear. So they will, when they pass each other. So this guy serves like a solstice because the gravitational wave has an energy equal mass. Mass actually interact with the energy. So that's like this wave will serve like a medium. This wave will actually the polarization will change. This is a physical model. Now the question is how do you define polarization? This is actually a strong field. Why not doing linear perturbation? Okay, so that's actually most of them be all okay, I'm going to consider geodesic devices. This is actually, even for the weak field, you can do the same thing. Here we should do from the measure point. Why? Because it's simple. You can do the same thing using linear perturbation like what we are going to introduce next class, geodesic device. This is rare definition. So then you just say, okay, I define this one. Then you know the title like what it says, not actually power return. In your Newtonian series, X, Y is a power return. So you have to consider this one. So that's why actually, this is spelling me actually about Wang, more than Wang. Interesting. How, okay. So then I say, okay, let's first choose the perfect. Once I choose any texture, that one is not a perfect, but I can make a rotation. Then perfect, then there are the angles. So I first define the angles of power in terms of not a perfect, then define the angle in terms of perfect. That angle actually gives you physically, because your current is perfect. It's unique, right? So that's okay. So this one here, this is just from measure component to give us directly intuition how things work. Real definition is geodesic device. That's why from very beginning this course, I emphasize a lot geodesic device. So in textbook, geodesic device is not so important. Why I emphasize it here? Because we use this to define geodesic parameters of geodesic device. Okay, so let's see. Once we have this one, you can see we have this only components, then we have this one. Now I can write the measure. Now we get everything in x double prime, right? I'm going to get rid of the x double prime. I just simply replace x double prime x. Let's do this double prime x. But you didn't remember, this is where we're working in this double prime. So then you can say ds squared equal dt squared minus dx squared minus dy squared minus dz squared. This is the background. Then linear perturbation, because this is going to be x squared. ds squared equal g equal h of eta ab plus epsilon h ab. X, A, X, D. So I simply drop the hollow term. Then plus this is H22 plus epsilon H22 dy squared, right? So it's H2, so plus 2 times epsilon H2 through dy dz. Then H through minus epsilon H2 to dy dz squared. Right? So this is our measure for the European width propagating on x direction. Now our idea is to study the physics meaning of H2 to H2, right? So I'm going to write here H2 equal dt squared minus dy squared minus dz squared minus dx squared plus epsilon H22 dy squared plus 2 H2 through dy dz squared minus So this is our measure. So what I'm going to actually do the following, because the linear, I first consider H2 3 equals 0. It's independent to components. I just consider the physical interpretation of H of n. In this case, I have actually the space-time. I have ds squared S squared equals dp squared minus dy squared minus, let's put that dx squared in front, minus dy squared minus d squared plus epsilon. Well, I just like to put x together. You see, minus 1 minus epsilon h22 dy square, right? It's a minus. Minus 1 plus epsilon h22 dz squared, right? So this is actually my measure for when h23 equals 0. I want to infer this. Okay? Then you see here. So if I consider, let's say, like what I said, this is actually my axis. This, let's see, don't want to make sure simple. This is my y-axis, this is z-axis, right? So let's see, this is our x direction, the floor is yz. And now if I cut around the floor to one circle, I need to try to write, look like circle. This is actually a circle, my circle never be circle, right? So this is circle before the gravitational comes. When the gravitational comes, so let's say this guy is, suppose let's say t equal 0 case, this is positive, right? What's this? This is proper distance on a y direction, right? Remember now we narrowed down our x, y that cannot change. The x, y that is fixed. So that means actually if this is actually positive, now this direction, y minus is small quantity, the proper distance becomes smaller. So I'm actually, this is actually y direction. This will squeeze it, something like this, smaller, right? The proper distance. Proper distance is t equals 0, y equals 0, z equals 0. This is the proper distance. Arrow y equals 1 minus h. This is the proper distance, right? If you want, I can start what? Let's say delta y equals 1. The proper distance becomes smaller. But here becomes lighter, right? So this angle will make the distance large. So what I observe is I will get something like ellipse, so along this direction, right? So let's say later, suppose this oscillating later becomes negative, then it's always cross, right? So always either the axis, this will become longer or this will become longer. But this is always the ellipse, the long distance either along the direction or y direction. So that's exactly what we call the path part of this. Okay? So if you put actually, like what I said, circle there, then there are no gravitational waves. I keep shooting my lasers back and forth. There are no phase difference. So in my screen, I cannot see any difference. So it's always the same waves oscillating. But once I actually, the gravitational pass through, you can see, normally I have sine wave, right? Suddenly pass through, I know this, the gravitational waves pass through. Why I know the gravitational wave pass through, like what I said, if electromagnetic wave pass through, actually from this circle, it's always to make the circle uniformly contracting. So because electromagnetic wave has energy. Energy is always positive, converting. So make it this is actually the test particle circle, right? Like the test particle moving in this direction. You flat, this actually circle will remain the same. But once you are in the energy, according to Hawking-Parnell's theorem, this actually converse will become smaller. But for electromagnetic wave, this is always positive energy. Corresponding to our R component always positive. Literally, we're saying this is 500 when I use the Newman Parnell. So this always makes it smaller. But only gravitational wave. Stretch one arm, squeeze another. So then I get something. So all the others I cannot see them. That's actually a unique feature. That's why we just put the two arms. So you can put the two arms, you can imagine you can put it separately. So the now why Lisa put a three of them? Lisa actually has three, right? So here only actually, in log only two or seven, because this is not for us. Why Lisa put a three? Because this is for equal actually two parents arms. They equal two lagos. Why we have lago India lago? Because we want to have different directions. This is actually India's ideal place to put another lago. So you can see easily polarization. For example, in the US I put this one, in the India I put this one, so like more like a circle. So if I put actually in principle the gravitational wave has maximum 6 polarizations. Actually, it's 4. You can say most general 0 is 6. So if I have 6 lagos in different places, I can measure precisely the polarization. Then I can test 0. Answer only 2. If I can observe more than 2, answer 0 is not correct. We need to multiply. That's why next generation is so important. So why we have been pushing to build more detector, because we want to get the polarization, to measure polarization. So the next generation actually of detectors, mainly, one of them is a major polarization. Like what I said, why so important? Different theory has different polarization. Einstein is a theory predict 5 polarizations independent. Brans-Digger theory actually has 3. Has 3 because you have scalar modes. This is called Brace modes. You can actually, GR has 2 plus scalar 3 modes. So different theory have different polarizations. If I can measure how many polarizations the gravitational has, then I can test the theory. So that's actually important. Another important theory is a nonlinear effect called memory effect. Memory effect is nonlinear. So memory effect, this is 2 arms. We think gravitational will pass through. It's just something like this, they will return. But nonlinear effect find, no, they will not return. The distance will slither forever. So this is actually nonlinear effect called memory effect. This is another goal to measure for the measurement of gravitational waves. Okay? So this actually you can see this plus the two actually we call cross components. This is just simply if I put it here, this the ellipse, the long axis is always either along y direction or z direction. Any other questions? Okay, now I'm going to this actually the H22 component. Let's come to the H23 component. The 2-3 components. Now let's say H23 different from 0, but H22 equal. Later you can put them together. In this case, dx squared is equal dt squared minus dx. Plus 2x. very simple, right? So what I'm going to do actually, I'm going to, this is my Z, this Y. I'm going to rotate it 45 degrees. Y prime, Z prime, this is exactly 45 degrees. Okay? If I do this, which means I'm going to enter, let's use actually height. So this actually, if I do y half equal minus y plus z, z bar equal minus 2. I use actually z equal y, either way is okay. In my notes, it's open. So it's just okay. That actually equation will become now you immediately see why I do this. I just actually rotate my coordinates so artificially, right? So what I do actually, if I do, I have this one. This is my y. This is my zx and yx, and simply this is y bar. This is z bar. You see here, if I simply replace H22 by H22, I get the same result, right? But not in terms of y bar and z bar. Which means, for example, if I want t equal t naught, if I H2 the positive, then these guys will stretch, right? So if I'm going to consider a circle like this. So before the gravitational pass this circle, but once it passes, let's say t equals 0 pass now the gravitational positive, this actually stretch here, right? So but squeeze here, stretch here along this direction because this guy is positive. So this section. Then you can see I will get something like, right? So later, for example, this guy becomes negative, then this will be a stress. This will be a squeeze. But in any case, you can see the x, the long x is always either along x bar, y bar, or z bar, which means 45 degrees. Remember, h bar, H22 is either along y or z, but here is along the axis 45 degrees. So that's why we say this is called cross parallel. This is the exact cross, 45 degrees. So we have cross parallel, this is 45 degrees. Einstein electromagnetic waves is also transversal, but it's 90 degrees. One is in y direction, another z direction. Gravitational wave is 45 degrees. Okay? So how you can see more clearly 45 degrees when we come back to see the geodetic waves, there you will see clearly this is 45 degrees because you need to make a rotation. Okay? Yeah. So, but this actually normally in a textbook we interpret the part this way. Like what I have been emphasized, really definitely use geodetic waves because you are very considerate the geodetic waves to arm. The distance between test part, the arms, each actual point is considered by test particle, right? So the two arms will not affect the gravitational waves we measure, right? The two arms also produce gravitational field. But
Why it
this
is L-shaped? Why it is L-shaped?
L-shape is like what I said. You can actually easily, actually, this is the interferometer max, 45 degrees. Yeah. So you can actually, that's a good question. The next generation of them, the U.S. is proposing, it's called aeroship. Aeroship, this actually is 40 kilometers, this is 20 kilometers. But the crater is 4 kilometers, 4 kilometers, it's a circle. The naked one, because the accuracy is high. This is technical. I just want to see this is what to do. Why technical, I have no idea. So the naked generation is still 90 degrees, but the two arms will be different. So this is 40, this is 20. This accuracy, this is increase in the accuracy. I do not take experiment how. This is actually called cosmic explorer. This is still actually not pure thing, it has not been supported yet. This is the U.S. idea. In Europe, they also propose this actually they use underground. This is a triangle. It's A, C. You can see each of them like arms. Now it's not actually 90 degrees, it's 60 degrees. So this is actually the European. This is called Einstein telescope. So this is ground, basically. These are painted all the triangle in the space. Why space is good? Because this actually, this actually 2.5 million kilometers. So this is very long. Very long, this is actually over zero, the gravitational waves were more wavelength. You know, when we measure this, gravitational waves are roughly equal in order of the arms, right? The arms were over zero. So these are over zero, actually large gravitational, long gravitational waves. For example, if you have two supermassive black holes, they produce gravitational waves. That gravitational waves exactly in the distance bound. So to observe gravitational waves exactly like an electromagnetic wave, you need to have two conditions. First, the signal is strong enough. Second, has to be in your observation band. If the signal is very high, but the frequency is very high, we cannot observe, like our ears. No matter how strong signal, if it's out of the band, we can hear it. Twice is not. The same thing for detector. Two conditions, signal strong enough. Second, the frequency is same band. So these are actually, in China there are two actually also projects. One is called Taiji, another Tianqi. Tianqi is actually, this actually leads actually with our sun as the center. It's called aerosurge orbit. So this is actually stable orbit. So Taiji is the Chinese, is actually about 3 million kilometers, larger than this one, but the orientation is perhaps a little bit different from LISA. They want to actually to test the difference, like what I said, like with India and Lago, so they want to observe the polar distance. Tianqi is actually the center of Earth. So there are some actually arguments because center of Earth, the noise is too big. But Tianqi seems they got a lot of money. The first phase they got actually, if I remember correctly, about 1 billion yuan, 1 billion yuan, yeah, 1 billion yuan, all in Tianqi. There was like a project 3 years ago from a Chinese technology ministry. They investigated like 1 billion yuan for both Taiyuan and Tianqi. So they are still in the phase study, like these are the most advanced. These are already have the first pathfinders in 2017 is better than what I expected. So US actually not said, okay, that's too costly. And the very beginning they called Lisa, then US will withdraw from project. European got angry, so okay, we're going to change the name. Lisa became an aegis. E means European. So after the 2017, NASA, the US said, okay, that's very good. We want to join again. So now, actually, again, NASA and the European join together. They come back with a Lisa to get rid of E. So I hope this will last. So there are competition between US, Europe, and also China. China actually want to build two. So I think it's not two. Finally, will be one. So this actually is the next generation, the space and the ground business. Also, Japan, so they have very high techniques. So we have LIGO, we have worked with the European. We also have like called GE 600. GE is the first generation, German and England. So,
Japan also has thermal.
yeah, German Dama is 200. Was you there in 1990?
No, I was in GIAN meeting in.
Oh, you were there?
Yeah.
Okay. So I was actually in Tama, actually, they had a meeting. So in 1999, it's the first time I went to Japan. So I was told a story. So they saw, because they tried to, they're small, this is 200 meters. US is 400 meters. So they built quickly, they want to first detect the Earth wheel to get a Nobel Prize. But I think that's very clever idea. So unfortunately, 200 meters, the sensitivity is not good enough. When I was there, this sort of parameter definitely is not a Gaussian wave. Because they find the signals so strong, it was crossing their head. They said, where does the signal come from? Even some people, the car passes through actually make a noise, but this totally take out. You know what's happening? They finally said, okay, there's a work actually about 2 meters wire. Oh, do we have or not? Okay.
Yeah, we can break now.
Okay, yeah.
I just want to add one thing.
Uh-huh.
The first LIGO meeting, the first meeting of LIGO, when
Uh-huh.
they were planning for LIGO,
Yeah.
was organized by me and Sanjay Dhingan at Jamia,
Oh, okay.
from Indian.
Okay, I
And
see.
all over scientists came from all over world. First
Uh-huh.
time it was in India International Center,
Uh-huh.
and 3 days conference,
Okay.
and 2 days were in Jamia.
Oh,
And
okay.
myself, Dhingan and Bala here,
Okay, I see. Yeah.
we organized that meeting. Although,
That's perfect.
yeah, it was only supporting, we were only supporting.
Uh-huh.
Supporting. The main people came all over, we provided our facilities.
Yeah.
It started here.
Good. Yeah.